Right, lesson 3.2, the derivative as a function. Whereas yesterday we looked at the derivative just where we plug in a as a constant. We're going to come out with a number, but today we're not. We're going to come out with it as a function. Then we're going to have differential functions. We're going to interpret it graphically, algebraically, and descriptively. We're going to obtain the derivative of a function by considering the derivative of a point and then treating it as a variable. How functions can fail to be differentiable. Sketching the derivative function given the graph of the original, and second and higher order derivatives. So let's look at three terms real quickly because we're going to use all three of these and they mean slightly different things. Differentiability means that the limit as h approaches 0 of f of x plus h minus f of x over h, that this exists. So as long as that limit exists, then we can find the derivative of the function. Now continuity is a little different. Continuity is that a function is continuous as if we can draw it without picking up a pencil. If we have to pick it up, then it's discontinuous. But that doesn't mean that it has a derivative everywhere. The existence of a limit is when, if we graphed a function and both of those sides are going into the same number. Now remember that f of that number doesn't have to exist, but the limit from both sides has to be going in. So three similar things that we're talking about, but not quite the same. They can be the same though. In section number 1, we found the derivative at a fixed number a. So we plugged in a number a into our difference quotient and we found it. But now let's say that a is going to vary. It's not going to stay the same every time. So replace a with an x and we get the function right here where x is going to vary. And so what that means, just reminding you, is that f prime, there's a prime here guys, so it's f prime of x, so which is the derivative of x. Geometrically, it's the slope of the tangent line at point x, f of x. So as the x value changes, the slope can change, and so that gives us a new function. So the derivative of f is the derivative because it has been derived from f by the limiting operation. And so the domain of the derivative of f is equal to x, the set of x, such that the derivative of x exists. And this could be smaller than the domain of f. It doesn't have to be, but it could be. So the first thing I'm going to look at is graphically how to sketch the derivative of a function. So anytime we have a tangent that is horizontal, that's going to be a 0. So I know this is going to be a 0 right here. And another thing that I'm looking at is the slope. So the slope right here, this is, the slope is all negative. And so it ends at 2, so I'm going to just kind of draw that line. The next one over here begins at 2. And so where the slope right here, the blue line I just drew, it is decreasing, so it's a negative slope, so it is going to be down in the negative part of the x below the, and it's going to be down this way. And it's slowly decreasing. So that's why the slope is slowly becoming less negative each time. Now right here, my slope is positive, and then it goes negative. So I'm going to have a positive slope, and then a negative slope. So positive slope, negative slope. It has to go through that 0, 0 because that's the tangent. Another thing I'm going to point out is that this is concave down, and so it's going to decrease. But it was a positive slope and then a negative slope. So positive side of the y-axis and then negative side of the y-axis. And then this last section, it is a positive slope. Now the slope's not constant, so it is going to, it's not going to stay flat. It's going to increase each time, but it's going to increase at a constant rate. And then from there, I'm going to take that one and I'm going to draw the second derivative. So this was the first derivative of it, and so I'm going to take this as if it were the new function, and I'm going to draw the second derivative right here. And so what I'm looking at right here, this slope, it's a negative slope the whole time. And the slope is actually a -2. So it's down here, it goes through -2. It stays constant. It's constant negative. And then this blue slope right here, it's a positive slope, and it's actually a +2 the whole time. This one's also a +2. And so that would be the slope of the second derivative. And I'm going to show you this. We'll talk about it in a minute. But see, there's two little apostrophes on that. That is the second derivative. And just so you've seen the first derivative, I went ahead and graphed it so you could see what it actually looked like, and that is what it looks like there. And the second derivative I didn't graph, but that's what it does look like, what I showed you in the previous slide. So just looking at this set of three graphs right here, what I'm seeing is that I've got a positive slope, so it's in the positive right here. See, it's never negative, so the slope's always positive. But what I notice about it is that in this first section, this is kind of concave down, so it's going down. And then it becomes concave up, so it goes up. There's this little turning point, but it's not horizontal tangent, so it doesn't cross the x-axis. So this is the first derivative. Sorry, this is the first derivative. And then from there, I'm going to look at the second derivative. This is a tangent that's horizontal, so it's a 0 right here. So those are the first things you always want to check for, is those horizontal tangents. And then it's concave up, so the increasing all the time. And this part's a negative slope, so it's down in the negative y. And then this half's a positive slope, so it's in the positive y. So here are three different functions. They're very similar if you look at them, but I'm going to find the derivative of each. I'm going to show you how to find the first one, and then I'm just going to show you what the second two are. So we're going to use our difference quotient, where it's equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. But we're going to remember replace that a with an x so that we can use it as a function instead of just a constant. So with that being said, we're going to go x plus h squared plus x plus h plus 2 minus x squared plus x plus 2. Now, of course, that's in parentheses. Be careful of that minus right there. All over h. So we're going to have to expand a lot. We'll move up. I'll move back down in a minute. This is an x squared plus 2xh plus h squared plus x plus h plus 2 minus x squared plus x plus 2 all over h. So a lot of this lesson is just being careful and doing things properly, which I did not because I have to distribute this negative in. So make sure you be careful with that negative that has to get distributed in. And then canceling out terms, because they should cancel out quite a bit of them. Then I get a 2xh plus h squared plus h all over h. And that reduces here. Oops, wrong h. Gone. Take one out of each. And this gives me a 2x plus h plus 1 all over 1, so I don't need that. And remember, this is when x goes to 0. So this h becomes 0. So this is a 2x plus 1. So remember that. That's the derivative. I'm going to come up and write it above it, and then I'm going to show you the other ones. So this is a 2x plus 1. This derivative is also a 2x plus 1. And this derivative is a 2x plus 2. So you can go through and try and see if you can get the same things, but they come out the same. That's what they will come out to. And what I want you to notice is that these constant terms right here don't affect what the derivative is. But notice this constant term was the same as the 2, but it did not come out to be the same. So just kind of pointing that out, keep that in your head. Constant terms end up canceling out, and so they don't affect the derivative. So here is our function f of x equals 5x minus 9x squared, and I want you to find a formula for the first derivative of x, and then if possible find the second derivative of the function. So I'm going to fill in my difference quotient, and so that's going to be a 5x plus h minus 9x plus h squared minus 5x minus 9x squared all over h. And remember, it's a limit as h goes to 0. So this becomes a 5x plus 5h minus 9x squared minus 18x h minus 9h squared minus 5x plus 10, not 10, minus 9x squared. All over h. Now, all that I did, I distributed here. I took and I foiled this. This is an x squared plus 2xh plus h squared. And I distributed the negative 9 into it. I distributed my negative across here. All right, now let's see what cancels out. Hopefully a couple terms. And they did. They should always have some terms cancel out. If you don't, you've done something wrong. So this is a 5h minus 18xh minus 9h squared all over h. Because at this point there should be an h in each term. And this becomes 5 minus 18x minus 9h. And it's the limit as h goes to 0. So now I can put a 0 in here. That cancels this term, and I have a 5 minus 18x. So this is my first derivative. I have my derivative of the function is equal to 5 minus 18x. Now I'm going to go ahead and do it again. I'm going to find the second derivative. So this is now the new function that I'm starting with. And so I have the limit as h goes to 0. And I'm going to do my difference quotient again. 5 minus 18x minus h minus 5 minus 18x all over h. So the limit as h goes to 0, distribute this in and distribute the negative. It's 5 minus 18x plus 18h minus 5 plus 18x all over h. Should have some stuff cancel out. And guess what? I do, because that's a plus, not a minus. Make sure. I'm left with 18h over h, which reduces to just an 18. There's no h in there, so my second derivative, f x equals 18. Except you need to be careful because we got to watch those signs. This was a plus, so this is going to be a minus. That's a minus. That's a negative 18. It's a negative. Be careful. Don't do what I just did. The last example was just a polynomial. So this one is a square root function. I want to show you a couple of options, a couple of different types of functions, and what will happen. So first thing I want you to look at, we're going to find the first derivative of g, but I want you to look at what the domain is on the first one. So the domain, remember, comes from what's underneath the radical, and that's going to be 1 plus 2x. It has to be greater than or equal to 0. So x has to be greater than or equal to negative 1/2. So that's our domain from the original function. Now let's find our derivative. So we have the limit as x goes, or not as x, as h goes to 0. It's not as x goes to 0, it's h goes to 0. And then of 1 plus 2, this is x plus h, minus the square root of 1 plus 2x all over h. So when I look at this, what am I going to have to do? Well, what I'm going to have to do is multiply by its conjugate. So I need to multiply the numerator and the denominator by 1 plus 2x plus h plus the square root of 1 plus 2x all over the same thing. Now, what you need to be aware of here is that if you have square roots in the numerator, you're probably going to have to multiply by the conjugate. But what's nice is that there's really not a whole lot of multiplying that has to go on, because they're conjugates. Multiply the first one, and what happens is the square root sign just goes away. And you multiply the last ones, and it's a minus sign, and what happens is the square root sign goes away again. And in the denominator, I am not going to multiply it out. I'm going to leave it, but I will go ahead and distribute this 2 into here, which I'm going to have to do in the numerator as well. And so right here, distribute is going to be a 1 plus 2x plus 2h minus 1 minus 2x all over h square root of 1 plus 2x plus 2h plus the square root of 1 plus 2x. So the 1's go, the 2x's go. I have this 2h left. I'm going to go ahead and reduce this, and then 2 over the square root of 1 plus 2x plus 2h plus the square root of 1 plus 2x. Now remember, this is the limit as h goes to 0, so this h is gone. What I'm left with, so don't forget that that h goes away. It's a pretty big deal. If you have an h left in the end, you've probably done something wrong. So this is 2 over, there's 2 of them, they're the same thing. And then I can reduce this set of 2's to give me 1 over the square root of 1 plus 2x. And so that's what the derivative is. Now let's look at the domain of this. It's a square root still, but it's in the denominator. So my domain on this one has to come from 1 plus 2x is greater than 0. So x has to be greater than negative 1/2. So for my derivative, the domain is actually smaller. I'm going to work one more for you and show you, because this is now a rational function. So we did a polynomial, we did a square root, and now we're going to look at the derivatives of rational functions. Again, we're going to do the same way. It's the limit as h goes to 0 of the difference quotient. So this is going to be a 3 plus x plus h over 1 minus 3 times x plus h. And then I'm going to leave a little space because I know what's coming. Minus 3 plus x over 1 minus 3x all over h. Now, what I want you to be aware of is that this all over h, you can actually also do all of it times 1 over h, which might be a little bit easier to see it that way. Now, in order to subtract these, I need to get the denominators the same, so I'm just going to take and multiply the fraction by what the other denominator is. So 1 minus 3x, 1 minus 3x, and then over here, 1 minus, I'm going to go ahead and distribute the 3 in, 1 minus 3x minus 3h over 1 minus 3x minus 3h. Now, I'm not going to multiply the denominators out because hopefully it's going to come out nice and neat, but I do need to multiply the numerators out. So I just need to multiply through. This is going to give me a 3 plus x plus h minus 9x minus 3x squared minus 3xh. And that's the first one. And then minus, this is going to be 3 plus x minus 9x minus 3x squared Move it over a little bit. Where was I at? Minus 9h minus 3xh. So that minus sign, I'm going to change everything behind it. And this is all over 1 minus 3x, 1 minus 3x minus 3h times h. All right, let's see what cancels out here. My first 3 is going to cancel. This one, and then the x and the minus x, minus 9x plus 9x, minus 3x squared plus 3x squared, minus 3xh plus 3xh. So what I'm left with in the numerator is then h and a 9h, that's a 10h over 1 minus 3x, 1 minus 3x minus 3h times the h, and then the h's will cancel here. Then I have 10 over 1 minus 3x, 1 minus 3x minus 3h, and this was again the limit as h goes to 0. So this is 0 because I plug in a 0 for the h, and it's gone. So this gives me 10 over 1 minus 3x, 1 minus 3x, oh, that's 2 of them. So 10 over 1 minus 3x squared. And then, let's see what the domain has to be. The domain comes from your denominator underneath radicals. There's no radical in this one. So it's the 1 minus 3x cannot equal 0. So x cannot equal 1/3 again. So it has the same domain. So now that we've looked at how to find derivatives for polynomials, for square roots, and for rational functions, let's just look at the different ways that we can say we're going to take a derivative. So notations for derivatives, we have our f prime of x. We can also just say a y prime. You can actually see it written this way, dy over dx, which is kind of common. And this is the Lebanese notation. Okay, and all that dy over dx means is the limit as the change in x goes to 0 of the change in y over the change in x, which is what we've been talking about the whole time. Right here it can be written as the derivative of the function over dx, or you can write it out here like this, the derivative, and put the functional notation behind it. You can also just have capital D in the front, or a D with that x because it was the derivative of x, of the function x. If you're going to take it at a specified number, it's going to be the same thing, but you just say x equals a, or down here written with the bracket. These are all meaning the same thing. So if you see any one of these, it's telling you the same thing. So just to point out again that the first lesson was talking about taking the derivative, and we were taking it at a specified number. So we just got a number back out. And this time we're finding new functions by taking the derivative of the original function. So what we're doing, we're finding derivatives, so we're differentiating. So a function is differentiable at a if f prime of a exists. So if f prime of a does not exist, we cannot find the derivative of it. And it is differentiable on an open interval, not a closed interval, an open interval, a to b, or it could be a to infinity, negative a to infinity, any of that. If it is differentiable at every number in the interval. So if it's not differentiable somewhere, then you can't take it. And so where is this function differentiable? So the domain of the original is negative infinity to positive infinity, but we want to look at our derivative here. So let's go ahead and look at that. So if x is greater than 0, then the absolute value of x is equal to x. But if x is less than 0, then the absolute value of x is equal to negative x. And so that's where this is going to come into play at. So we're going to find f prime of x, and that's the limit as h goes to 0, and then it comes out to be x plus h minus x over h, which is equal to just 1. So this is for when x is greater than 0. But if x is less than 0, it comes out to be the limit as h goes to 0. It's the negative of x plus h minus a negative x all over h, which just reduces out to negative h over h, which gives us a negative 1. So what that tells me is that there's a left-handed and then there's a right-handed. So the limit as it's coming from the positive side, so the limit as h goes to 0 from the positive side is equal to 1, but the limit as h goes to 0 from the negative side is equal to negative 1. So if I were to draw the graph of the derivative, I would have this. And if you notice that, this is a jump. So it's discontinuous. So it is not differentiable everywhere. It is not differentiable at 0. We're going to look at that in just a second. The original function, it's an absolute value function, so it looked like this. If you remember this right here, this is called a cusp. So my formula for f prime of x, or the derivative of x, is two-sided. So it's a jump. It's a discontinuous function. So it's positive 1 when x is greater than 0, and it's negative 1 when x is less than 0. So what this leads to is that not every function is differentiable. But if a function is differentiable, differentiable functions are continuous. But not all continuous functions are differentiable. Because the original one, the absolute value function, it was a continuous function, but it's not differentiable. So this leads us to this theorem. If f is differentiable at a, then f is continuous at a. So the ones that are not differentiable are functions with a bend or a cusp or corner, if they have a jump discontinuity, or if they have a vertical tangent. They may be continuous functions, but those functions are not differentiable at the point of the bend, the cusp or corner, the jump discontinuity, or the vertical tangent. So this is a corner or a cusp, and you cannot take the derivative right here. You can't take the derivative at a jump discontinuity. And this one's the one that people forget about is, or, well, all of them, but a vertical tangent, because the slope here is undefined. This function is continuous. It looks smooth. There's no like crazy looking stuff on it. But a vertical tangent is an undefined slope, so you cannot take the derivative at that point. So looking at the function right here, it's the square root of the absolute value of x. Is this function differentiable everywhere? And then if it's not, where is it not differentiable at? And why? Why is it not differentiable if there's a spot? Let me know. The next thing I want you guys to try is to try to find the derivative of this function. And then once you get that, see if you can find what the second derivative is. And then see if you can take the derivative of that one and see what the third one is. So try those three and then answer the question and tell me what you got. So we can take the derivative of any amount of time that we want. So if I wanted to take the fifth derivative, I could write it like that. I could write 1, 2, 3, 4, 5 of x. I could write d5y over dx5. So just in general, you can take any the derivative any amount of times that you want. The last thing we're going to look at is the position function and seeing how this can be applied in a physical situation. So if I am given a function for the position of an object over time, so distance equals rate times time, then I have my first function. And then the first derivative that I can take of that would be the velocity function. So this is in meters. This would be like meters per second. And then the next one, the next derivative, the second derivative I take is the acceleration function. And its units would be meters per second squared. And then the third derivative, it's actually, of course, the first derivative of the acceleration function, is the jerk function. It's the rate of change in the acceleration. And what this leads to is a sudden change in acceleration caused by an abrupt movement of the vehicle. So when you feel your vehicle jerk, when you accelerate real fast or something, that's the jerk function. And what do you think the units for that last one would be? You tell me in this last question.